Data structures. So there are many ways in which we could categorize data, but here we're going to look at four broad categories that characterize the type of data commonly used in applied work. So some notation first. Let W denote the set of variables of interest. So we have a response Y and covariates x1 through to xk. And let S denote a sample from the population probability distribution of these variables governed by some parameter vector theta. Four common data structures encountered in practice. The first common data structure is called cross-sectional data, obtained by observing the sample at a single point in time, t, with observations indexed by I, where I takes a value from 1 to n. So cross-sectional data give us a snapshot of a population or some phenomena at a single point in time. Each observation represents a different unit, that could be some entity or an individual. And this is the typical data structure derived from surveys, including census data. That would give us a data sample that reflects census households, for instance, at one single point in time. That's cross-sectional data, one single point in time. Time series data, the second category I want to look at, is obtained by observing a single unit at successive time points, in this case indexed by t. And t could be minutes, it could be hours, it could be days, it could be years. So time series observations can be ordered chronologically, and this structure is useful for reviewing trends, pattern, and seasonality. So we could look at time series data for weather, for instance. It could be traffic flow on a link. It could be the number of passengers on London Underground over a day or over a year. That would be typical examples of time series data. So one observation observed at multiple points in time, indexed by t, where t can take a value from 1 up to big T. The third data structure that I want to talk about is called longitudinal or panel data. And this is obtained by first selecting a sample S and by then collecting data on that same sample at multiple time points. And notice how there are now two dimensions to the data. There is a cross-sectional dimension indexed by I, and there is a time dimension that's indexed by T. So panel data are essentially a combination of cross-section and time series data, but crucially, they follow the same units over time. That allows the analysis of individual level changes and trends over time, and it allows us to study dynamic behaviour across units for the same units over time. So mixing both temporal and cross-sectional observations, but always for the same units. And finally, the fourth structure I want to talk about is called repeated cross-section data. This is obtained by taking a sequence of independent samples at different points in time and then simply stacking them together. It also has two dimensions of variation, cross-section and time, but crucially we don't necessarily observe the same units over time because it's independent samples that are taken at each point in time. So we may observe the same units, but we might not. So think of something like a typical national census that's taken in many countries. The census samples households, let's say, in 2001, and the 2011 census sampled households again, but not necessarily the same one. So a unit in repeated cross-section data may appear at more than one time point, or it may appear only once in the data. We don't necessarily follow the same units over time. And repeated cross-section data are useful in allowing the analysis of change without following the same units, and they're also useful still for studying trends and comparing time periods, particularly for average values. So here's an example of a typical applied data set that will hopefully demonstrate what I mean by these data structures. Here we have urban mobility data that's been collected for 101 US cities from the period 1980 to 2017, and it's been updated annually. So you can see the cities listed here under urban areas: Akron, Ohio, Albany, New York, Albuquerque, New Mexico, and so on. These cities are observed over years, listed here, with information on the population the city had, the number of commuters, daily vehicle miles travelled on both freeway and arterial roads. So this is an example, of course, of a longitudinal data set. The same cross-sectional data, that is, these 101 cities, are observed over time annually for 38 years. And notice the relationship with the other structures. If we were to extract one single year from the longitudinal data set, then we would have a cross-section data set for 101 units. If we were to extract a single city, say Akron, Ohio, and we would have a time series data set for Akron, Ohio from 1980 to 2017. Now the key point of this section is as follows. Data structure has implications for the assumption of independence of observations, and violations of this assumption that the observations are IID, that is, independent and identically distributed, are common in 4 settings. First of all, in time series data, so observations sampled at different points in time may not be independent because past values influence present values. And we've talked about that previously when we introduced the concept of autocorrelation. So an example would be child height. Clearly, the height of a child is dependent through time of the same child. Second, we have spatial data in which cross-sectional observations are sampled spatially, and that may exhibit spatial autocorrelation when geographic proximity influences values. So if we think of a weather map, nearby places tend to have far more similar weather than further away places. Third, experimental design. Sometimes experiments produce clustered or hierarchical data where relations within clusters can induce dependency. And finally, we have repeated measure data. So that's longitudinal data falls under this category, where the same subjects are measured repeatedly over time or under different conditions, and we would expect observations on the same subject to be dependent. We wouldn't expect them to be independent. So the methods described in lectures 4, 5, and 6 for calculating uncertainty measures, standard errors, and so on are not applicable where data are dependent. And that's the problem that this lecture is addressing, and it's doing so within the context of a mixed model.